I'm going to record this, but everything I write down, I will send to you in a PDF format after class. So you'll have everything I write down, provided to you later. Okay. Now let's do the derivative again. All right. So we have both derivatives ready to go. So for my second derivative, I'm going to use a power rule again, right? And take these powers and drop them out front. So I have 10/3. I multiply that times -1/3, x to the -4/3, because I'm subtracting 1, right, from that. I'm subtracting 1 from -1/3. Then I have -10/3. I bring out 2/3. Now this becomes x to the -1/3. Cleaning that up, I have -10/9. X to the -4/3, then minus 20/9, x to the -1/3. Any questions here? If you came in a little bit late, the reason why everyone has their videos on is because I offered to drop your lowest quiz grade and replace it with 100 if you turn your video on today. So if you didn't catch that, just restating that. Okay, here we go. Now, to figure out where the function is going up and down, we need to take the first derivative, we need to figure out where it's 0, and we need to figure out where it doesn't exist, right? So let's take a look at this first derivative. I have the fortune of being able to copy and paste, so I'm just going to do that here. Here's my first derivative. I want to figure out where this derivative is 0, where this derivative doesn't exist. All right, so to figure out where the derivative is 0, I need to set it equal to 0. And this is where things are going to start getting messy. That does not look like an equation that you would look at and just be like, oh yeah, I don't mind solving that, right? I mean, that's somewhat nasty looking, right? So to do this, I'm going to just follow through a couple of algebra moves first to see if you follow this. I'm going to take on this first one, I'm going to rewrite it as 10 over 3x to the 1/3, then minus 10 x to the 2/3 over 3 equals 0. So all I did there was I took the x to the -1/3, I dropped it down to the bottom, right? And then over here, I brought this x to 2/3 and I just brought it up on the top with the 10. Now, the reason I did that is because I'm about to put these together into get a common denominator, and put these two fractions together into one fraction. So I needed to be very explicit about what was in the numerator, what was in the denominator. So my common denominator, to put these together, my common denominator is 3x to the 1/3. So I need to make sure both denominators have that in there. And I can see that on my second fraction, I'm missing an x to the 1/3 here. This first fraction, I have the whole thing there. So I need to multiply the top and bottom of this fraction by x to the 1/3. Just on this fraction, right? And that will give me the common denominator I'm looking for. I think I'll do that over here on the side. X to the 1/3, let me do the top, times 10 times x to the 2/3. On the bottom, I'm doing the 3 times x to the 1/3. So I'm just doing this over here. What do I get on top?
10x.
10x, right? Because when you multiply these two together, you add their exponents. And 1/3 plus 2/3 is 1, right? 3/3. So that turns into just 10x on top, which is really nice. And so here's where I am. I've got 10 over 3x to the 1/3, that's the first fraction, minus 10x over 3x to the 1/3 equals 0. And so now I combine them together into one fraction. 10 minus 10x over 3x to the 1/3 equals 0. And the whole point of that was to go back to that thing that we've been talking about in this class. That's anytime you have a fraction equal 0, you only have to look at when the top is 0. So from here, I just set the top equal to 0. And that I should be able to solve pretty easily. I'll add 10x to both sides. I'll divide both sides by 10. And I get a really nice answer that x equals 1. So that's a critical number. Any questions here? Y'all hang tight. I'm just going to go get a cough drop real quick. Well, while I'm doing that, why don't y'all think about where the derivative would not exist, right? Look at that derivative. Think about where it possibly would not exist. And I'll come back and I'll ask y'all what you think. All right, so what are your thoughts here on this not existing thing?
X cannot equal 0.
Yeah,
Does-
x can't be 0.
Yeah,
So it's not obvious. It's not obvious from this one. But if you go down and look at the derivative down here when we cleaned it up and we put everything together, I hope it's clear that you can't have 0 down here, right? Because then you'll have division by 0. Now, you could have seen that right here, but you would have to realize that's 1 over x to the 1/3. And then you realize, okay, you can't have 0 there because you'll have division by 0. So I'm thinking x can't be 0. So that would be a second critical number. But remember, with critical numbers, you always have to go back and look at whether or not these numbers were in the original domain of the original function, right? So let's go back to the original function right here. Are there any domain problems here? So are there any numbers you can't plug in? Notice we don't have any negative exponents there. So those x's are not on the bottom, are they? Right? So we don't have to worry about division by 0 with the original function. Also, x to the 2/3 really means the cube root of x squared. X to the 5/3 really means the cube root of x to the 5th. So we don't have to worry about negative numbers, because remember we said that if we have a cube root, right, an odd root, it's okay to have positives or negatives underneath. We just can't have square roots or even roots. Then that's when we have to worry about negative numbers. So would you all agree that the domain of this is everything, all real numbers, the original function, right? Which means that both of those points, both of those values, one and negative one that we got, are going to be critical numbers. Any questions there? Okay, then let's continue. What do I do once I find the critical numbers? Oh, remember?
Plug them into the original equation, right? Or am I wrong?
So that's if we had if we had a closed interval, right? And we were trying to find the absolute max and min, then here's where we would plug them into the original function. Then we would plug in the two endpoints, right? We'd figure out what the highest and lowest values were. That's what we do for closed interval method. But when we're just trying to figure out where a function is going up and down in local maxes and local mins, this is where we need to draw the number line. And we have to pick test points. That's ring a bell?
Don't you plug them into the derivative?
The
At the
test
test
points,
points,
yeah,
the
the
test
test
point.
points will go into the derivative.
But
Exactly.
the x equals 1 will go into the original function, I believe.
When we actually go to find, if we determine that we have a maximum at 1, we'll plug 1 into the function, original function, to figure out what that maximum value is.
Right.
But we need to figure out what's happening first. So I have two values, 0 and 1, right? Those are my two. Those are my two critical numbers. Now I pick test points, something to the left of 0, something between here and here, something here. How about -1? That seems reasonable. Between 0 and 1, like a half. To the right of 1, how about 2? Those are my test points. I have 3 of them. And these go into f prime, okay? Your test points go into the derivative. Why? Well, because we're trying to, the derivative tells us if we're going up or down, right? If the derivative is positive, our function goes up. If the derivative is negative, our function goes down. So we need to know, is it positive or negative, right? The derivative. So my derivative is on the other page. Let me go grab my derivative. I could grab this one, but I really, again, think it's best to grab this one. Not the whole thing equal to 0, just the derivative itself cleaned up. I'm going to grab that. And that's the one that I'm going to be plugging into. So let me write this down here. This right here is my derivative. So let's plug in some numbers. If I plug in to this -1, I'm going to get on top 10 minus 10 times -1. All over 3 times -1 to the 1/3 power. On the top, this is 20, right? That turns out to be 10 plus 10. On the bottom, remember that this here really means the cube root of -1. So one number times itself 3 times gives you -1, -1, right? So on the bottom, we get 3 times -1. So this winds up being a negative number. That's all I care about. A positive number divided by a negative number. So that tells me over here on my number line that the derivative over here is negative, right? Which tells me my original function is doing what over here?
Pointing down.
Yeah, going down, right? If your derivative is negative, that means your function goes down over here. And now we have to do the same thing for the remaining test points. Let's plug in a half. So 10 minus 10 times a half over 3. I'm going to write it this way. The cube root of a half, because that's what the bottom really means. The top is 10 minus 5. And the bottom, do y'all agree that the bottom is a positive number? I mean, that's the most important thing here. The cube root of a half, I don't know, it's some number I can get on my calculator, but the important thing is that it's a positive number. And I'm multiplying it times 3, that's still positive. So I have a positive on top and bottom, which means that the ratio here is positive. That tells me my derivative over here is positive, which means my original function is going up here. Hey, we go down and then we go up, right? That's going to be a local minimum at 0. I can see right now it's a local minimum. All right, now let's plug in 2. What happens when we plug in 2? Well, we got 10, take away 20 over a positive number again. I'm moving a little faster there. Right, when I plug in 2 here, on top I get 20, 10 minus 20, that's -10. On the bottom, again, it doesn't matter. I'm taking the cube root of 2, which is some positive number, times 3 is still positive. So I wind up getting a negative over a positive, which is negative. And that tells me here that my derivative is negative, which means my original function is now going down. So you can see that from the left side of 1, I was going up, the right side of 1, I'm going down. So I'm going to have a local maximum there, right? I think we can answer part A and part B now. Part A, when is the function going up? Okay, it's going up between here and here, right? That's where the graph's going up. So the way I say that is using interval notation. I say between 0 and 1. And remember, this is an interval, not a point. I was talking to one of my colleagues about this the other day. How the notation for intervals and points is confusing the students. There's an easy way to distinguish the two. Not all textbooks do it. But if you want to do that and not have to worry about being clear on that, here's what you do. If you write in front of it X, and then this little symbol right here, that little symbol means element of. So what you're saying is that for the graph is going up whenever X is an element of this interval. That I'm just sharing this with you. That's all. You don't need to do it on the test. If you just give me 0, 1, I'm happy. All right, now where's the function going down? All right, so it's going down. That's happening in the green regions, right? Forever that way. And to the right, forever that way. So I would write that this way. Negative infinity to 0, union 1 to infinity. Any questions yet?
How many of these are going to be on the test? Like these increasing, decreasing problems?
Well, I mean, we could probably only have one, considering how much other information there is on this test, right? And there's a lot on this test. So probably only one, it'll probably be pretty basic. Now on your final, you might have a more complicated one. Part B, local max, local min. Start with local max. Well, I have a local max. Where is it happening? What's the X value of where I have a maximum?
At 1.
At 1, right? Because the graph goes up and then down. You can imagine the graph goes up and then it has to come back down here, right? Over here, it goes down and has to go back up. So I have a local max here at 1. So I'm going to put 1 here. And then what I want to do is get the Y value. I'm going to write this as a point, not an interval. So how do I figure out the Y value at this point?
Plug it into the original.
To the original function. So the way I'm going to be clear about that is I'm going to write 1 f of 1. That way you know I'm about to plug 1 into the original function. And now I need to go back to the original function, which was way over here, right? This is it right here. Oops. Let me grab that. Just so we have it. When I plug 1 into this function, let's see, what would happen if I plug 1 into that right there? Well, 1 raised to any power, right? 1 raised to any power should still be 1. So both of these parts, when I plug in 1 in for the X, those are both going to turn into 1. So isn't that just 5 minus 2? Which is just 3. So I just get 3 here. Oh. Where do we have a local minimum? We actually do have one, right? It happens when you plug 0 into the function. So this happens when I plug in 0, and then I plug 0 into the original function. That's 0 and then 0. Because when you plug 0 in for X here, it kills off both of those terms. There we go. Okay. All right. We're like halfway through, right? A little more than halfway, but we now need to do the parts C and D, which have to do with the second derivative, not the first derivative. So we're basically going to do everything we just did with number line and test points, everything we just did, but we're going to do it with the second derivative. So now let me go back and let me go grab that second derivative. Here it was. And let me see, should I? Yeah, so we're now doing the concavity part, right? Right, this is the second part of this. We're going to take the second derivative. We're going to figure out where the second derivative equals 0, and we're going to figure out where the second derivative doesn't exist. So let's start by setting it equal to 0. Now, because of what we already did, when I write this first line down, maybe you'll understand where I'm going with this. So wherever I had those negative exponents, I dropped the things down. Any questions on that? We need a common denominator. They both have 9s, so I don't have to worry about a number. One of them is x to the 4/3, the other one's x to the 1/3. So a common denominator would be x to the 4/3. So how could I change this x to the 1/3 to an x to the 4/3? What would I have to multiply it by?
X
X to what power?
first.
The first? Or you could
Oh,
say, yeah,
Three-
that's right. 3/3, right? X to the 3/3. Because when you add them together, you get 4/3, wouldn't you? But x to the 3/3 is the same as x. So I'm doing x. Basically, I'm multiplying the top and bottom of that second fraction by x. And that turns out to be really nice because now what I get is the -10 from the first fraction minus 20x from the second fraction over the common denominator of 9x to the 4/3. That needs to be equal to 0. But for that to be 0, I just have to set the top equal to 0. And then if I solve that, I think I get x is -1/2. Divide both sides by -20. Any questions on that? We're good? All right, let me do something real quick. I'm gonna take a real quick screenshot so I can see. Everyone here had their video on, so I just want to make sure I have that on record. See, wasn't that an easy 100? All right, how about where the derivative doesn't exist? The second derivative, where does that not exist?
Zero.
Yeah, I'd look at this one here in green. 0 again, right? For the same reason as before. So x equals 0. So we have two critical numbers. I'm going to draw them on a number line right here. I have -1/2. And I have 0. Make sure you put those in the right order, right? If you get the order wrong, you're in trouble there. Test points, -1 here. Way over here, +1. Between these two, I don't know, -1/4. Where am I plugging those test points in?
The derivative,
Which one?
the second one.
The second one, right? Because I'm interested in the concavity here. So my second derivative is the one I just did in green here. I would like us to think about this for a second before we start plugging things into it. Look at the bottom of this thing. What does x to the 4/3 really mean? What root is that? David's saying that's the cube root, right? Third root,
Cube root of x to the fourth.
x to the 4th. Okay, what can you tell me about x to the 4th? It will always be what?
Positive.
Positive, right? And its cube root of a positive number is positive. So do y'all agree that no matter what I do, my denominator is always positive? So all I really care about then is what the numerator is doing, right? Whatever the numerator does is what this second derivative does. Okay, so imagine, let's see if we can do this just visually. Imagine I take -1 here and I plug it in for x right there. I'll have -10 minus 20 times -1. What would that be? Positive or negative?
Positive.
Positive, right? Positive. So that means if I plug -1 into the second derivative, my second derivative will be positive. What does that tell me about the original function? Remember concavity, happy people, sad people, right? So my original function is doing what here?
Caving up.
Yeah, concave up. Like this. So it looks like a smile. Now imagine plugging in, let's do 1 over here to the right because that's easier. What if I replace that with a 1? We'll have -10 minus 20. That'll be negative, won't it? -10 minus 20 will be negative. So over here on the right, we have the second derivative will be negative over here, which means my original function is not happy, right? It's concave down. What about -1/4? Let me do that one by hand. If I take that one, plug it into derivative, I get -10 minus 20 times -1/4. That's -10 minus, well, actually, it's going to become plus, isn't it? Because I have two negatives there. So plus 5, right? Because 20 divided by 4 is 5. And that's a negative number, right? My denominator was positive. So I don't even care about the denominator. So that means my second derivative here is also negative, right? Just like it was to the right of 0. And I told y'all in class before that you cannot just get the first one and then just assume that they're just going to keep switching each time. But you have to check each one, right? This is a perfect example. We have concave down twice, don't we? Concave down, concave down. All right, I think we can answer part C of the problem. Part C, where's this function concave up? Well, let's see, that's happening to the left of a half, right? So that'll be -infinity. I said to the left of -1/2. I think I said +1/2. Right, to the left of -1/2, we are concave up. And then we are concave down. Actually, we're concave down to the right of -1/2 the whole time. So we can say from -1/2 to infinity.
We don't have to exclude 0 on that interval.
Good question. I was wondering if anyone was going to ask me. No, we do not. Because let me show you the picture. And then once I show you the picture, maybe it'll make a little more sense why we don't have to. Now, we would have to exclude 0 and do 2 different intervals if 0 was not in the domain of the original function. We would. But the thing about increasing and decreasing is that you need, in order to talk about something going up or down, you have to have 2 points to compare things to. So this is why I told you when you're doing increase, decrease, always to use open intervals, and that using a closed doesn't change anything. It's because you need two points to talk about up and down. So excluding the endpoint It's just one single point that you can never, I guess what I'm trying to tell you is this. If I go to 0 right there, right? I can't tell you that the function is increasing or decreasing there. I can't talk about what's happening at a single point. I can only talk about what's happening at an interval. So let me show you the picture, but let's get part D first before we do the picture. How about inflection points? I think I called them just IP in the class last time. Do we have any inflection points? What are inflection points?
Where the concavity changes.
Anywhere the concavity changes. Anywhere we have a change. And we only have one, don't we? And -0.5. So I only have one. So what I'm going to do is I'm going to say -0.5. And then I'm actually going to find the point on the function. So what I'm going to do is I'm going to plug -1/2 into the original function. Now that's going to suck because I'm probably going to need a calculator to do that. Where's the original function? I used it earlier. Here it was. I probably need a calculator to do this. That didn't help. This problem has only taken us 40 minutes. Let's see here. I'd have to plug in -1/2 in here, which would be F. I have 5. Then I'd have the cube root of -1/2 squared minus 2 times the cube root of -1/2 to the 5th power. So I'd probably need a calculator for that. So I'm going to hold off on it because I'm going to use the computer to do it for me. But you could do that on your calculator and get a decimal answer. All right, let's look at the graph of this. There we go. F of x equals 5x raised to the 2/3 minus 2x raised to the 5/3. Huh. Interesting graph. What I do like about doing this through Zoom is my ability to like easily integrate things onto the screen. It's a lot better. Okay, so check this out. Let's talk about where the graph's going up and down. All right. So up, where's it going up? Looks like increasing from about here to here. In that green region, the graph's going up, right? It's going down here and here. Is that what we got? Were we increasing between 0 and 1? I think so, if you go back and look, right? Were we decreasing to the left of 0 and to the right of 1? We should have been. Let me see, I'm going to go back and look at my answers here. Where were we increasing? We are increasing between 0 and 1 and decreasing to the left of 0 and to the right of 1. So that matches the graph, right? And then, how about concavity? Oh, wait, how about local max and local min? Did we have a local min at 0, 0? I think we did, right? 0, 0, that's a local minimum. And we had a local maximum here. That matches, right? All right, next thing, concavity. Where am I frowning and where am I smiling? Let me do frowns first. Do you agree that all of this is a frown? That's all frown? Okay. Now the next part's hard to see. really hard to see. But from here to here is frown, and here over is smile. It's really hard to see that, but I know that because of our calculus, right? The calculus says that there's this point right here, right? This was -0.5. Right there is where we have this change in concavity. To the left, we're concave up. To the right, we're concave down. Kind of hard to see that from the graph, isn't it? Kind of hard. Let me go back over here. Maybe there's a way I could do this to really make it obvious. I don't know if I can. Let's see here. Trying to see if there's any way I can change this shape. I don't think there is. Yeah, even if I do that, it's hard to see it. So we have to trust the calculus, I guess, huh? All right, what do y'all think? Any questions? All right. So we're supposed to do 2 more of these. I'm not sure how that's going to happen. So let me do this. Let's start the next section, and then we'll go look at the 2 problems. All right. So let me blow my nose. You'll hang on. Okay. So the next section is called curve sketching. And the way that you need to think about this is, I mean, like right now, if we want to graph a function, we're going to go to Desmos, we're going to go to a computer, to graph a function, right? But historically, it's only within the last, decade that graphing has become so easy to do. Like, I realize there's been graphing calculators, right? But even those are a little bit non-user friendly. The fact that we have a website we can go to and just do it easily is something new. But before computers, how did we graph things, right? How did we graph them? We didn't sit there and just do like t-tables and plug in 1,000 points, right? What we do is calculus. This is exactly what we would do. We would use the derivatives to help figure out what the shapes of the graphs were, and then we would draw the functions by hand. All right, very tedious, very cumbersome, very time consuming. But before computers, this is all we had, right? So historically, this is a huge section in a calculus course because this is where we bring everything together. And when I say everything, I mean everything. Back to college algebra, we bring it all together and we say, how do we graph functions? Curve sketching. So this is the steps, right? All this section is about is how do we sketch curves? How do we bring all the techniques that we've learned throughout our whole lives into a final technique? So what we do first, if we're given a function, is we find the domain of the function. Then we do some college algebra stuff. We find the x and the y intercepts. Do you remember doing that in college algebra? How do you find the x-intercepts of a function? Set it equal to 0, right? Set it equal to 0. How do you find the y-intercept? You plug 0 into the function. That's college algebra, right? Then we check for symmetry. That means we can check to see, is this an even function? Is it an odd function? If it is, then we have possibly, the picture looks like a reflection of itself. We think about that. We discover any asymptotes. Does it have any vertical asymptotes? Does it have any horizontal asymptotes, right? Then we start kicking in step 4, we can kick in calculus there too, because we've found asymptotes in this class by taking limits as x goes to infinity and negative infinity. That tells us what's happening at the end of the function. So we can start using calculus in step 4 to find asymptotes. Step 5, we figure out where the function is going up and down or where it might be constant. That's what we've just been doing. We find any local maximums and minimums. That's what we were just doing. We figure out where we have inflection points, and that means we're gonna have to figure out where the function is concave up and concave down. And then we somehow put all this information together in a table, and then we draw the curve. Right? That's what we do. Now, what I want to do is just present one problem where we do the whole method on this, and then we move on. Because realistically, right, in 2022, you're never going to need to sketch a function in detail by hand, right? Never. Because we have the computer to do it for us. But we do need to go through one example where we just use all the methods together, all right? Everything, we bring it all together. All right, so I'd like to do that. I'd like to do a problem like that right now, all right? So I'm going to follow these steps for a problem I'm just going to make up on the fly here. You ready? Use methods from algebra, calculus to sketch f of x equals x cubed minus 16x. I'm keeping it simple, all right, because I don't want us to get bogged down with the derivatives and setting them equal to 0. I just want you to see the whole thing come together into one piece, all right? All right, first step. What's the domain of this function?
All real numbers.
All real numbers. Good. All right. That's the first step. After we figure out the domain, we're going to figure out any x and y intercepts. All right, let's do that. X intercepts. To do that, we set the original function equal to 0, right? So to do that, I'm going to take x cubed minus 16x, set it equal to 0. I can factor an x out, which leaves me x squared minus 16. And then I can recognize that x squared minus 16 is a difference of squares. I have 3 x-intercepts, 0, -4, and +4. We good? All right, y-intercepts. You will only ever have one y-intercept on a function. So to do this, what we do is we plug 0 into the function. And if you plug 0 into this function, you get 0. So you only have one y-intercept. So far, okay? Check for symmetry. So here's what I'm going to check for. I'm going to do this right here. Symmetry. So first thing I'm going to ask myself, question, is this even? Oops. Is it an even function? Right? Is this an even function? So what does it mean to be even? I'm basically asking this, is f of x equal to f of negative x? That's the definition of an even function. So when I plug in x, do I get the same thing as when I plug in negative x? Well, f of x is just x cubed minus 16x. Is that equal to negative x cubed minus 16 times negative x. So all I've done here is I've replaced all my x's with negative x. So x cubed minus 16x, is that equal to, well, what is negative x cubed? What's negative x times negative x times negative x? It's still negative, isn't it? Right? It's still negative x cubed. Now, what about negative 16 times negative x? That would be plus 16. Are those the same? Oh, sorry, I forgot the x. Are these the same? No. So is it even? No. Now, had it been even, okay, had it been even, then that would have mean that it was a reflection over the y-axis. That's what it would have meant. Even functions are reflections over the y-axis. So I would know that when I draw it, whatever it looks like to the right of the y-axis. Wait, did I just say x-axis? I meant to say even functions are reflection over the y-axis, not x-axis. Why would I ever say that? Okay. All even functions are reflections over the y-axis, right? If this had turned out to be true, I would know that. So when I'm drawing it, I'm looking for that, all right? So now I ask myself, is it odd? Is it odd? So is this true? Is f of negative x equal to negative f of x? That's what it means for a function to be odd. That when you plug in negative x, you don't get the original function, but you get the opposite, right? The opposite of the original function. So we already did this. When we plugged in negative x, we got negative x cubed plus 16x. Is that the same as putting a negative in front of the original function? Is it or is it not? What do y'all think? I see some
Yeah,
nods.
it is.
It is. This is the same thing, isn't it? Once I distribute that negative through, we're going to have these both these are going to be equal. So it's odd. It's an odd function. What does that mean? Even functions are reflections over the y-axis. Does anyone know what an odd function would look like?
It's symmetrical over the origin.
Over the origin. Very good. That's what we call it. But what it really means is it's a double reflection. It's a reflection over the y, then a reflection over x. So let me give you an example. If I gave you a function, I told you it was odd. Let's say I told you this function was odd and it looked like this. Okay? Let's say it looked like that. Then to the left of the y-axis, it would be a reflection here, like this. But then reflect that over the x-axis. So that's what it would look like. That's what an odd function would look like. You take the right side of it, you reflect it over the y and then the x. That's called reflection over the origin. You could also look at it as a rotation of 180 degrees. If that doesn't make sense to you, take this piece in blue and rotate it by 180 degrees. Flip it like that, and then it becomes the other piece. Okay, so we know that our function, whatever it looks like to the right of the y-axis, it'll be that double reflection to the left of the y-axis. All right, what next? We could have put this in Desmos a long time ago, right? And been done. All right, find any asymptotes. Find any asymptotes. This is step 4. We have 2 types of asymptotes that we look for, vertical and horizontal. So how about vertical ones first? All right, so for vertical asymptotes, what I'm doing is I'm looking at the original function here in yellow, and I'm asking myself, do I ever plug a number into that would give me a 0 on the bottom and a fixed number on top, not 0 over 0. A fixed number on top and then 0 on the bottom. Would that ever happen? Well, we don't even have a fraction, right? So we don't have to worry about it. So there are none here for this particular problem. But you could have another problem, like I'll just show you a real quick example here in the corner. Let's say I had this function f of x equals 3 plus x over x minus 4. This would have a vertical asymptote at x equals 4. Why? Well, because when you plug 4 in, you get 7 on top and you get 0 on the bottom. 7 over 0 is undefined. So at 4, there's something crazy happening. So what we would have to do is take a limit as x approaches 4 from the left and right to figure out, which way the graph is going. But I'm just giving you an example of one that would have a problem. All right, this one doesn't have a problem. Now for horizontal, what I'm going to do is I'm going to use calculus for this. I'm going to take the limit as x goes to infinity of the original function. So what I'm doing here is I'm saying, hey, if you look at this original function, I want to know what's happening as you go out to the right forever. Like, what does it do, right? Does it go out, does it flatten out? What happens? So you take the limit. This will tell you what's happening out the right side. And can y'all see what we're getting if we let x go to infinity? What type of form do we see there? That goes to infinity, right?
Infinity minus infinity.
Minus infinity, right? Good. Infinity minus infinity is an indeterminate form. So how do we get around that? Well, there's a couple of ways, but in this one, do y'all see there's kind of an obvious way? Not obvious, I shouldn't say obvious. Unless you remember how I told you to attack infinity minus infinity. Your favorite F word? Second favorite F word?
Factor.
Factor.
Factor. Pull the x out. We're left with x squared minus 16. Now take the limit. What happens? Infinity times infinity. What's infinity times infinity? Infinity, right? So does this have a horizontal asymptote? Is that headed to a number? No. But what it does tell me is that when I go to draw this function, what is it going to be doing as I go to the right? The further I go to the right, what does the graph do? I should expect it to go up, right? I should expect the graph to go up as I go to the right. And then we do the same thing. Let's figure out what's happening out the left side. So that was me going out the right. Okay, this is getting the right behavior. Do y'all see that I'm acting like we don't have a computer, right? We don't have a graphing calculator. We're back in the 1960s right now. And we're like, what does this graph look like? And I'm trying to put all these little things together that I've learned, right? To get a good idea of what this looks like. Limit x goes to negative infinity. Let's go out the left side. And let's go ahead and factor it right now. Where does this go? Where am I headed? Yeah, okay.
Negative infinity.
That goes to negative infinity. Good. Times now, what about this? Be careful. You're going negative infinity squared, which is positive, right? Minus 16 doesn't matter. So this goes to positive infinity. And now you have a negative infinity times a positive infinity. That should be a huge negative number. Which means that when I graph this and when we go out to the left, we should expect this thing to be going down like that. Now I realize, okay, I realize that in college algebra, you're taught how to figure this out for polynomials. Like, I understand that in college algebra, they tell you, hey, look at the degree and then look at the leading coefficient. And then what you do is you use this thing called the leading coefficient test. If the degree is odd and the leading coefficient is positive, then your left side goes down, your right side goes up. I got it. I understand that. I'm giving you a generic basic example so that you can see how we use this procedure. I didn't want to start with like a hard function that you can't use anything that you've learned in the past on. I want to give it something that you're familiar with. So that's why I did this example. Okay. What's next? Asymptotes. Okay, finally, where's the function going up? Where's it going down? All right, so we're going to bring in some derivatives now. What's step 5? So I'm going to figure out where the function's going up, where the function's going down. So let's take our derivative of our function. Okay, our function here is this 3x squared minus 16, right? That's our derivative. All right, I want to know when that derivative is 0. I want to know when that derivative doesn't exist. To see where it's 0 should be pretty straightforward. I can just move 16 over to the other side, divide by 3, take the square root. I get 2 answers. Don't forget, it's 2 answers because you're taking the square root, plus or minus 16 over 3. I'm going to go ahead and get that on my calculator just so I have a decimal, so I have some idea of where it is on the number line. 16, divide that by 3. I get approximately plus or minus 2.31. And of course, those are critical numbers because the domain of the original function was all real numbers. Does the derivative ever not exist? Well, the derivative is a nice quadratic, right? It's defined everywhere, so this is not a problem. Now what?
Number line.
Number line, test points, up, down, right? That's what we're doing next. Negative root 16 over 3, positive root 16 over 3. Those are my only critical numbers. I need test points here, here, and here. Good test points I should use. I don't know, negative. I'll go -4. 0 is a good one here. +4. See, that's why I think it's important. I mean, that's why I went and found what this was as a decimal. So it'd be easy for me to figure out what my test points should be. Where do those points get plugged in? Derivative, right? Now I'm just going to get these answers for you, okay? Is that all right with everyone? If I just get these answers? It should be positive, negative, positive. All right. Which means that our original function's going up here, then our original function's going down, and then our original function goes up. You with me? I'm just going to leave it like this. I can tell, well, maybe y'all will agree with me on this or not. Do you agree that from that table, I have all the information I need in terms of when the graph goes up and down and where I might have local maxes and mins? It's all visually represented there, right? So I'm not going to write all that down at this point. I'm just going to kind of leave that as it is. And I'm going to move on to the second derivative and get the table for that, get the little chart, and then we'll continue and proceed. Any questions? All right, so let me go back here. So 6, I'm skipping the local max and mins. I'm skipping it. I'm moving to where it's going up and down. So 7, I want to figure out where the graph goes up and where the graph goes down. concave up, sorry, concave up, concave down. So I need to take the derivative again, don't I? The second derivative, so here's my first derivative. The derivative of this is just 6x. Very nice derivative. Hey, out of curiosity, what if our second derivative was just the number 6? Not 6x, but just 6. What would that tell you about the function? In terms of concavity?
Is it constant?
It would be, okay, so if I said that, if I told you that the second derivative of some function was 6, what can you tell me about the concavity of the original function? That it's what? Well, is 6 a positive or a negative number?
Positive.
Positive, right? This is a positive number. And if the second derivative is positive, that means that your function is concave up. And that means it would be concave up the entire time, wouldn't it? Wouldn't it? This might blow your mind a little bit, maybe not. Check this out. Let's go back to the good old, I'm going off topic here for a second. Let's go back to the good old quadratic function, right? A parabola either opens up or down, right? Up or down. Concave up, concave down. And what determines it for a parabola? What do we always look at to see if it's concave up or down? We look at A, don't we? Right? Whatever the value of A is, determines if it's concave up or down. Well, why? Take the derivative. What's the derivative of this function? 2ax plus b, right? Take the derivative again. What's the derivative of that? 2a, right? But see, this tells you if you're concave up or down. So if a is positive, then that's a positive number and you're concave up. If a is negative, then that's your second derivative is a negative number and then you're concave down. So a dictates the parabola, doesn't it? Does that kind of make sense? I'm off topic, sorry. Okay, separate idea. All right, so for us, the second derivative is 6x. So what I'm going to do now is I'm going to figure out where the second derivative is 0. I'm going to figure out where the second derivative doesn't exist. Let's take care of that one first. That's never going to happen because the second derivative is 6x. It's a very nice, very well-behaved function. I set the second derivative equal to 0. I get 0. Nice, clean, easy answer. I draw a number line. I put 0 on here. I pick 2 test points, -1, +1, and I plug those test points into the second derivative. That's what happens. If you plug in -1 into this derivative, second derivative, you get -6, which means my original function is concave down. If you plug +1 into the second derivative, you get +6. That means my function is concave up there. So negative, positive. Okay, y'all good up to this point? We're almost done. Do y'all remember me telling you that story about that guy that came into the tutoring lab when I was in graduate school, getting all pissed off at me about me not like getting a problem wrong and I needed to explain it to the class? Remember that story, kind of? And I told you that he called me Bobby and we had the Bobby method. Remember that thing? This is what it is right here. All right. This is the way that this is the way that makes sense to me in terms of putting all this information together to draw a picture. Okay. Textbooks will use something called sign charts to do this, which I just don't like the sign charts. I think it's confusing. At least as a student, I thought it was confusing. So let me just show you the way that I now put this all together. All right, you ready? Start with a new page. I'm gonna use graph paper. I know this is kind of cheating because not all of you have graph paper with you. I'm just doing this to help me line things up, okay? So if you don't have graph paper, don't worry about it. So what I'm gonna do is I'm gonna start with a number line. Let me go smaller graph paper. Start with a number line. Here's 0. All right. Now, I want you to remind me, because I don't have it in front of me here, what were our critical numbers from the first derivative? When we took our first derivative, we set it equal to 0. What did we have? Was it that root 16 over 3 one, positive and negative? Yeah, that was it. Okay, so 0 wasn't on there, but I'll just leave that there. We had positive root 16 over 3. And then we had negative root 16 over 3. I don't even care where these are really. I'm throwing them on here. All right. So those in yellow were the critical numbers from the first derivative, right? What was the critical number from the second derivative? 0, right? The 0, which I happen to put there already. Okay. All right, so what I'm doing here in this first step is I'm drawing a number line. I'm putting all the critical numbers from the first and second derivatives. And what that does is it now breaks up this. I'm about to make a chart. I'm not using dotted lines here, okay, because this isn't test points and all that. I'm not doing that. I'm going to draw a chart. And this chart is going to have 3 rows to it. The first row is going to be the information I have about the first derivative. The second row is going to be the second derivative's information. And the third row is going to be me putting those two together to give me my final information about what the function f looks like. So let's start with our first derivative, this bottom row. I'll give you a second to catch up. All right, on this bottom row, I'm going to go back to the picture I had for the first derivative, right? Because that's what I'm focusing my attention on right now, first derivative. My picture of the first derivative was this one right here, right? So I was going up as long as I was to the left of this. And then between here and here, I was down the whole time. And then to the right, I went up again, to the right of root 16 over 3. So watch how I'm going to put this together. I'm going up here, down here, still down, and then up, right? So to the left of the yellow, I'm up. Between these two yellows, I'm down. To the right of the yellow, I'm up. Now for the second derivative, to the left of 0, I'm concave down. To the right of 0, I'm concave up. To the left of 0, concave down. Right of 0, concave up. Questions there? Final thing, let's talk about f. To figure out what's happening here, what I need to do is put these two pieces of information together. I must be going up, but I must also look like a frown. So think about a frown. On a frown, on the left-hand side, you're going up, but the right-hand side, you're going down, right? So the only way to be going up a frown is to be the left side of a frown, right? So that tells me that my original function must look like the left side of, ooh, that's not very good. Must look like the left side of a frown. That's what's happening to the left of negative root 16 over 3. My graph looks like the left side of a frown. Now, between root 16, negative root 16 over 3 and 0, between here and here, I need to be going down the frown, which means I must look like the right-hand side of the frown. Then from 0 to here, root 16 over 3, must be going down a smile. So when you think about a smile, on the left-hand side, you go down, on the right-hand side, you go up, right? So the only way to be going down, but still be on the smile, is to be on which side?
The left side.
Left, yeah, so you gotta look like the left side of a smile. And then over here, you must be going up the smile, which means you must be going on the right-hand side. Does that make sense to you all? All right. We're getting there. Time to put it all together. Final picture. The real graph. Notice I'm lining things up vertically. This is my y-axis. Right here at 0, right? Here's my x-axis. Shit. Can't even draw a straight line. All right. I'm going to put the points I have here, root 16 over 3, 0, negative root 16 over 3. Let's go back to the beginning. First step, domain. I know that my picture goes in both directions forever. Second step, x-intercepts at 0, negative 4, and 4. Let's go put them on the graph. 0's here. 4, remember this number? This was like 2 point something, right? So 4 is over here. Negative 4 is over here. Those are x-intercepts. Those are points on the function that are touching the x-axis. Right? Y-intercept. So I've got those. The y-intercept is 0. I already had that, don't I? On my picture, it's right there in the center. So I've got the y-intercept drawn. Asymptotes. No vertical ones. Oh, wait, I forgot the even odd. I'm odd, so I've got to remember when I draw this, the right side, the left side are reflections over the origin. Just going to remember that when I draw it. I know that the right side goes up, left side goes down. Hey, couldn't I have figured this shit out by knowing that it was odd? If the right side goes up, then the left side has to go down because it's a reflection over the origin. It's going to have to do that. I could have, but I didn't. All right. And then the rest was the up and down. So I think now what I would do is I would actually figure out, I would take these points. Well, these and this one, I would plug those into the original function. And those would give me hard points, wouldn't they? And what I'm going to figure out when I plug this in, I'm going to get some point up here. I'll figure it out in a second. And then over here, I'm gonna get some point over here like this. Y'all trust me that that's what would happen? And once I have that, I can draw the picture. Because I know that to the left, over here in this region, right? Over in this region, which really means over in this region over here, it's gonna have to look like the left side of a frown. So my graph is going to look like this, but I've got to go through that x-intercept. And it's going to have to continue going down forever. And then between this negative root 16 over 3 and 0, it must look like the right side of a frown. Till it gets here. Now it turns into the left-hand side of a smile. That's an inflection point, by the way. And then it turns into the right-hand side of the smile and it goes up through the x-intercept. Now I still need to figure out what those values are, but that I would have to plug into my calculator to figure out, or just do it by hand. There you go. That is a very accurate drawing of that polynomial function. I can tell you the x-intercepts. I can tell you the end behavior. I can see the symmetry. I know where the local max and mins occur. I can talk about where the inflection is, concave up, concave down, right? It's all built in there. Now, that's not the type of function we would really want this for, right? Like, this is not a hard function to graph. A hard function to graph are the problems that come from that section. Like, where are they? These are the problems out of that section, 4.4. So I'd say like the first few are straightforward because they're all polynomials. Those are all like happy zone, you know? Yeah, even this one's good. These aren't that bad as well. I mean, these are all polynomials. So all of those together are like reasonable functions. Then shit starts getting crazier because now you start having like rational functions. Imagine you need the first and second derivatives of those, right? All of these difficult problems because the derivatives are harder to deal with. And then you get into even crazier problems, right? We have roots involved. Imagine the first and second derivatives of those. Hey, that looks familiar. That one looks familiar. Right? Isn't that the problem we started with? We had done this problem, right? We had done that problem earlier. And we had all the information we needed. When we did that problem, we had all the information we needed to do the Bobby method, where you draw the table and figure out what's going on. We had everything, we just need to put it together. We just hadn't looked at domain, symmetry, all the other things. And then you get some trig functions involved. So what am I going to expect you to do? Well, on this test coming up, nothing in terms of drawing the whole picture. Okay. I'm not going to want that. What I am going to want on this upcoming test is what we started this class with it. And that's, I give you a function, you tell me where it goes up and down, give me local max and mins, tell me where it's concave up, concave down, give me any inflection points. I'm not going to ask you to bring it all together and draw me a picture. It takes too long. And the other part takes too long as well. But okay, any questions? I want to try and squeeze one more in here. We have 15 minutes. We hadn't done 34, 36. Did I give you all these for homework the other day? I need to look real quick. What are your homework out of? Let me see these. So from your homework set, the only problems that are assigned, this is 4.3 I'm talking about. The only ones that were assigned were 31, 33, and 35. Those are the ones that are assigned from here, which is good. I think you should do those. I think you should do, you know, these as well, just to practice. You know, shit, do them all. I don't know. I mean, you know, you have to manage your own time. So given that those are probably done by me on video, the ones in blue, let's take a look. Let's see if we can knock out this one real quick. Okay, let's see if we can knock out this here. So we want to, for this one, we want to figure out where it's going up and down, local max, local min, concave up, concave down, inflections. All right, so let's take derivatives. Let's use S because they use S of X. Let's just use S the whole time. The derivative of this is 1 minus cosine X. That's our derivative, right? Our second derivative is sine X. right? Because you have to take derivative of 1, which is 0. The derivative of cosine x is negative sine x, but there was already a minus sign there, so that's why it became plus. Are we good on first and second derivatives? No questions? Okay. Let's figure out where the function is going up and down. So I'm going to take my first derivative. Where's the first derivative? 0. Where does it not exist? By the way, did y'all notice that they gave you a domain restriction to start the problem? Y'all see that? 0 to 4 pi. They restricted the domain to start. All right, so let's figure out where the derivative is 0. Here's a derivative. Set it equal to 0. Add cosine x to both sides. So you want to know where cosine of x is equal to 1. And you're only looking between 0 and 4 pi. So this goes back to your understanding of pre-cal. The way that I teach my pre-cal students is to look at the unit circle. Cosine is the x coordinate, right, on the unit circle. So you're asking, when is the x coordinate 1? And that only happens at one point, and that's right there. That angle that corresponds to that point is the angle, well, there's a few of them. There's an infinite number of angles. But 0 is one angle that would give you that answer. 2 pi is another one, and 4 pi. Those are the only answers between 0 and 4 pi. Y'all understand what I'm doing here? Going to the unit circle. When is cosine of the angle 1? That's whenever we are here at this point, because the x coordinate is 1. And then we ask, what is the angle? So it's either the angle is either 0, or you can go all the way around, that's 2 pi, or you can go around twice, which would be 4 pi. And I only look between 0 and 4 pi. Technically, there's an infinite number of answers. How about where the derivative doesn't exist? 1 minus cosine x. Cosine is defined everywhere. So there's no problems here. So we only have these critical numbers. So now draw a number line. 0, 2 pi, 4 pi, right? Now you might start saying, okay, I need test point here, 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 but you can throw away this and this because you're only looking between 0 and 4 pi. So you only need 2 test points. How about pi and 3 pi? Those are good ones. And those numbers get plugged into D,
The
no, not original.
The first derivative.
First derivative. Be careful here. The biggest problem that I run into with students on this next test is knowing when to plug things into the original function versus the derivative, right? The only time we plug into the original function is if we're doing closed interval method 4.1, or we're actually finding the local maxes and mins or inflection points. All test points go into derivatives, either the first or the second. Say it again. All test points go into derivatives. All right, so I'm plugging into the first derivative. This means 1 minus cosine of pi, right? What is cosine of pi?
Negative.
-1. Cosine of pi is -1. Right? Pi, the unit circle, pi is over here. Cosine of pi is the x coordinate there, which is -1. So this becomes 2. All I care about is that it's positive, because that tells me my original function over here is going up. And then when you plug in 3 pi, hey, what do you get when you plug in 3 pi?
The
Same
same.
answer, right? Same thing. See, it doesn't switch. Positive again. Do we have any local maximums? Local
No.
minimums? Nope. Not on that interval, right? No local max, no local min. It goes up. Where is it increasing? Well, between 0 and 4 pi. It's increasing between 0 and 4 pi. Where is it decreasing? Never, right? Well, I'd say never, not on this interval, right? Not on this interval. Can I proceed? Because I'm really close on time here. I'm going to do the second derivative now. So now I'm taking my second derivative. I want to know where it's 0. I want the second derivative. I want to know where it doesn't exist. My second derivative, we said was sine x.
Actually, can I ask a quick question about the intervals?
Yes, please do.
Really fast, just briefly. Would we end parentheses or would it be brackets because it's restricted in the domain?
If I were writing the answer, where is this function increasing? I would write 0 to 4 pi. Now, that's because I've told you, whenever you do increase, decrease, just always do open intervals. It would
Okay.
not be wrong to put brackets here because you actually can include the 2 endpoints. But like I've said before, 1 point doesn't change the increasing or decreasing. It doesn't change by taking out the endpoints. It doesn't like make the increasing and decreasing not valid anymore.
Right. Thank you, sir.
Yep. And if you're saying, where is it decreasing? Does anyone know how you say that there's no answer here? Anyone know the technical way to say no answer when you're talking about intervals and sets? We haven't talked about this before. Ariana, does your cat know by chance? Did your cat just jump up there? I thought the cat wanted to participate. So this is the way we say the set that has nothing in it. It's a 0 with a line through it. Now, for those of you who are military, that's the way you write the number 0 in the military, right? You write it that way so that you don't confuse it with O. But in math, that's actually referred to as the empty set. The empty set. The way that I think about the empty set is, let's say you have a bag. That's a bag. Sorry, it's a terrible bag. And that bag has all the answers to some equation. So let's say I take an equation like x squared minus 4 equals 0. The solutions to that are 2 and -2. So I'd have the number 2 and the number -2 in that bag, right? So the answers live in that bag. Imagine the bag holds the answers, okay? What if you have no answers? How do you say that? Well, you say that my bag is empty, right? The set of answers, the bag that contains my answers is an empty bag. This is the notation we use for an empty bag. So if I'm trying to tell you, hey, where does the function go down? I'm trying to tell you, hey, there are no x values. Wherever it goes down, then I write the empty set. I transgress. I'm going off topic. I want to get back to this because I have 3 minutes. I'm trying to figure out where the second derivative is 0, where it doesn't exist. I'll kill off the doesn't exist because it's the sine function. The sine function is defined everywhere. I don't have any issues with it. Where is it 0 though? Now I go to the unit circle again. Sine is which coordinate? X or Y?
Y.
Y. Where is the Y coordinate 0 on the unit circle?
0 and pi.
0 and pi. There are 2 answers, right? Or 2 dots on the unit circle. So now I need to list out all of the answers, all the angles that correspond to those 2 dots between 0 and 4 pi. So I can start with 0, that's this angle. Then I can rotate to here, that's pi. Then I can go around, that's 2 pi. I can go around again, that's 3 pi. And I can go around to here, that's 4 pi, and that's where I stop. I have a lot of answers here, 5 of them. So I draw a number line, I have less than 2 minutes. I start here at 0, I end at 4 pi. Here's 2 pi. Here's pi. Here's 3 pi. And this breaks my number line up. But I don't have to look over here and I don't have to look over here. I need to pick test points here, 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 here. I pick them. Pi over 2 is a good one. 3 pi over 2 is a good one. How do I pick another one? Does anyone know how to find? Does anybody know how to find the number right in the middle of 2 other numbers? I give you 2 numbers on number line, do y'all know how to find the one right in the middle of them?
I mean, it's 5 pi over 2, right? But
Take their average. Anytime you're given 2 numbers and you want to find the number right in the middle, like if I give you 2 pi and 3 pi and ask you to find the number in the middle, you take the 2 numbers, add them up, and divide by 2. That gives you the average of the 2 numbers. And that right there is 5 pi over 2. If I wanted to find the number right in the middle of 3 pi and 4 pi, I'd add them, divide by 2, 7 pi over 2. All right, then you got to plug those in. I'm out of time. But you will get, you should get concave up. So you should get a positive when you plug in that one, then down, then up, then down. I'm not showing that, okay? I do want to show you the graph of this, x minus sine x. I just want to show you the graph so we can see it. If you got to go, you got to go. Y equals x minus sine x, but I want to restrict this between 0 less than or equal to x less than or equal to 4 pi. Oops. And let's go to a standard view here. Kind of cool. Yeah. That's the graph. Notice it's always increasing, right? It's always increasing. And then it looks like right, always increasing. We knew that when we did the first derivative. We said it's always increasing, never decreasing. But in terms of concavity, looks like smile till about right there. And then it looks like it's frown until about, I don't know, somewhere around here. And then maybe it looks like smile again. And then frown. Do y'all see that? Smile, frown, smile, frown. Maybe I'll go back here. I can change my thing to, oh, pi over 2. Yeah, now you can really see it. Y'all are like, hurry up, I'm ready to go. Yeah, now you can see it though, because you got smile to there, smile here. Notice that's between 0 and pi, you're concave up, between 2 pi and 3 pi, you're concave up. And then you're concave down from pi to 2 pi to 3 pi to 4 pi, which is exactly what we got here. Concave up, down, down. Okay, so what we're done. What is your homework? What do you need to be doing before next class? You need to be doing, the big thing is this section here, derivatives in the shapes of graphs. And I would be focusing most of my attention on the problems in the latter section, in the 30s. All right. And then if you want to start some of the curve sketching, those are good for just, because to do the curve sketching problems, you can do some of those but don't do the entire curve sketching. Just do the increase, decrease, like up, down, concave up, concave down, right? Don't do all the symmetry and all that other stuff. It's just a good set of problems for you to kind of practice this whole technique over and over and over on different types of functions. Do y'all follow what I'm getting at here? Okay, I'll see you on Thursday. My plan is to be in class. I think I've been without fever, so I'll be good. Thank you for doing this. I didn't want to lose a day and I didn't want to have a sub because that can always be, I'm wind up having to go redo it anyway. So y'all have a good day. Appreciate you showing up.